pore pressure measurement. So we're not going to get into detail of this, but there are various elements of seals. There are piezoelectric elements. There are strain gauges essentially used to measure sleeve friction, tip stress, and pore pressure. So that's what a typical CPT would look like. Now, some key points I mentioned. Well, this is, of course, historically developed by the Dutch. The advantage of CPT is you get continuous profiles of strength and stiffness. Just like SPT, we can correlate friction, sleeve friction, tip stress, and pore pressure with engineering parameters that are useful for us to assess whether ground improvement was successful. Now, the charm of SPT is perhaps you can, let's say you have a ground like this full of MD, marine deposits, and you have lenses of silt. So let's say this is silt, this is sand, this is silt. So the charm of a CPT is as you push it into the ground, you can actually detect these lenses of silt and sand because it's continuous. Whereas if you were boring drill holes, you might flush this out and entirely miss it. So if you look at a continuous profile from CPT readings, you can catch these nice lenses of sands and silt, which might help to explain some geotechnical anomalies on site sometimes. So that's the charm of a continuous profile. You can also use CPTs for not just geotechnical applications, but for environmental applications. You can measure the pH. You can measure other environmental parameters for site characterization as well, and the discontinuous lenses, as I just mentioned. CPT probes are generally 36 millimeters in diameter with a cross-sectional head of 10 centimeters squared. The typical shape of the cone, it has a 60-degree apex. So the apex is this 60-degree apex. And I showed you other configurations, but the most commonly used one is this 36 millimeter diameter, 10 centimeters squared, 60-degree apex. And the typical loading rate is about 10 to 20 millimeters per second, so it's quite slow. So it's a quasi-static test. It's a penetration test, but quasi-static. The cone penetrometer that I showed you is heavily instrumented. You have load cells, which are strain gauges, full bridge strain gauges, to measure sleeve, friction, tip stress. And you can also have piezoelectric elements to get the pore pressure. So these are just fancy words for measuring pore pressure, sleeve friction, and tip stress. And we'll talk about how we use these measured parameters to get geotechnical properties. Other important points that I want to bring up, there are different names for CPT. If they can be used to measure pore pressure, you might see them called piezo cells as well. Some CPTs that measure pore pressure are also called CPTU. The U is, of course, for pore pressure. The presence of pore pressure measurement is quite useful. Sometimes you can hold the CPT at a particular depth, and when you push it in, you'll generate excess pore pressures, right? You can hold it and see how long it takes to dissipate these pore pressures, right? Then you can estimate the permeability of the soil. You can even use it to get consolidation parameters. So think about how. If you do this in situ, it's quite useful. As I mentioned, it can be quite useful for environmental assessments. You can get gamma. Gamma is very similar to nuclear densometer when we talk about compaction. You can shoot gamma waves rays out to see the degree of compaction as well. You get pH, salinity, and temperature. You can install all these onto your probes. These are quite versatile. You can put these onto barges or ships, so you can get offshore marine deposit strength and stiffness profiles as well. And cone resistance can be correlated, it's empirical, can be correlated to bearing capacity, density, and strength parameters as well. The core limitation of CPT is perhaps if you run into very granular material, core stones, boulders, then you're not going to be able to push it through, then you have to extract, find another location, and penetrate further. This CPT test, as we've discussed quite a bit, is quite suitable for marine deposits, for land reclamation, but you won't see this being used for CDG slopes or ground material, or weathered rocks of Hong Kong. To show you some realistic pictures of it, this is a Fugro truck for mobile CPT testing. It can be checked up, provide a bit of reaction. Inside these trucks is a frame to provide reaction to push this cone in. You don't need a lot often. So this is the truck. It can be stabilized with these stabilizers. Inside there's a loading frame. These are 1 meter rods. You can just keep on attaching with the threads, the 1 meter rods on, and the cables will come out to give you real-time data acquisition for friction, tip stress, and pore pressure response. And you can see that this is the rod coming out from under the truck here into the ground. So that's typically what happens, and you can have some sort of user interface for data acquisition, which is often in terms of depth. So you can get those parameters that I mentioned in terms of depth. Now for CPT testing, what can we measure? Well, we can measure verticality. There are inclinometers inside these cones. We can get pore pressure with piezo cones, as I talked about. Soil resistivity can give you indications of permeability or environmental parameters. You can also use it for PVD, ground vibration. Geophones, same thing as when we carry out very dynamic things on site. We usually measure the PVD, the particle velocity, using geophones. We can use gamma ray backscatter for density. Remember the compaction lecture, we talked about backscattering for nuclear densometer. Some devices can also give you pressurometer values. What is that? Well, some devices can actually expand. If you expand, what can you get? Well, you can probably get K0 values at rest pressure as well. Compressibility as well. If there's an element that can expand, you can do acoustic penetrometers, so geophysics means so you can send a wave, see how long it takes to reflect back. If you know the speed of the wave, you know the distance, you know the time, then you can use it to do something such as the shear modulus of the soil. Right? So there are various things that CPT can measure. It's quite versatile, as you can see. And as I mentioned, there's also CPTU or piezo cones, more or less the same thing. Piezo cones can be quite useful by getting pore pressure response. The first is the advantage of having pore pressure measurements is detecting the thin layers of silt and sand I talked about. Now, how do you do that? Well, if you have a thin layer of sand, the permeability will definitely be more pervious compared to the clay. So leading up to this lens of sand, you'll see pore pressures drop because of higher permeability. So if you're looking at a continuous pore pressure profile, you'll see it drop suddenly as it passes a lens of sand, and that can be used for profiling. You can use that to identify thin layers of sand and silt. Likewise, if you can hold a CPT with pore pressure measurement at a particular depth, you can deduce the permeability. If you know the permeability, you can guess what type of soil it is. Well, we talked about 10 to the minus 3 meters per second is probably coarse grained material, 10 to the minus 9, and less is probably clay, and something between silt, right? So you can use that to determine the soil type. You can also get static pore pressure. So if you want to know what's the in situ pore pressure, it could be in excess, could be hydrostatic. You just hold the probe there, as I mentioned, and you can deliberately wait for pore pressures to dissipate. When you push the cone in the ground, you will generate excess pore pressures. And if you wait for it to dissipate, you can treat this like a permeability measurement, or you can treat it like a odometer or consolidation related parameters. and that's 0.4. Essentially, you can get the coefficient of consolidation if you know from built. So that's the essence of a CPTU and the advantage of it. Here's a more close-up of the piezo cone or CPTU. We have pore pressure element just behind the cone here, and this is a standard 36 millimeter cone with an area of 10 centimeters squared. And we are again measuring sleeve friction, tip resistance uncorrected, and some devices have multiple piezoelectric or pore pressure measurements as a redundancy. Dynamically, it requires time to equalize, so it's nice to have additional pore pressure transducers to cross-check. And of course, these pore pressure devices can be at the tip, on the cone, or just behind the cone. That's how you measure the pore pressure. Now, with cone penetration, let me pop this up. There are three parameters that we can measure. You remember, I mentioned it's the cone tip stress, right? Cone tip stress is QC. We know the force we're applying because we're controlling the reaction inside the truck. We have a load cell frame. We know how much force we're applying, and we know the area of the cone, right? 10 centimeters squared. So we know the cone resistance, and beyond that, we have load cell at the cone tip, so we know the load. So QC is one of the main parameters that we can use. Of course, we mentioned that there can be pore pressures acting downwards on your cone because pore pressure is isotropic. So you can apply a correction factor to this, semi-empirical. In soft soils, at extreme depths, you might need to correct for overburden as well. So the cone resistance can be corrected in terms of the pore pressure acting behind it, and also this effective overburden. So we just take our measured cone resistance minus the overburden of the soil above it. And this, of course, is total stress, right? Because why is it total stress? Well, with CPT, we assume it's in clay. In clay, of course, it's undrained. And it's undrained, we're probably dealing with the total stress in the area. So it's not the effective overburden. So that's one of the parameters we can deduce. The second parameter is the sleeve friction resistance. Again, this is quite straightforward. We have load cells on the sleeve, so we know the frictional force acting on the sleeve around the cone. We know the area of the sleeve, so we can deduce the sleeve frictional stress. Now, we often have additional parameter called the friction ratio. What is that? Well, we take the sleeve stress and divide it by cone resistance, so Q subscript S over QC. And you often see correlations with friction ratio. Why am I talking about these parameters? Well, just like SPT testing with the N, with CPT testing, we also need some measured parameters to correlate with geotechnical parameters. And it so turns out that in CPT testing, we use cone resistance, sleeve friction resistance, and friction ratio instead of a single N value. You could say it's more robust, but it adds some complexities, right? Now, some researchers in the early 1980s have also proposed additional parameters based on these cone resistance and sleeve resistance. For example, Roth proposed that we can play around with the different resistance from the tip and the sleeve, and we can actually come up with 3 more parameters. So these are normalized. Roth suggested that we have to compensate for the increasing overburden as we get deeper in the ground with our measurements. So Roth proposed 3 parameters, uppercase Q, F, and B, which are normalized. Cone resistance, normalized friction ratio, and normalized pore pressure. And what are they normalized by? Well, some correction related to the overburden. We don't really have to understand the details of this, but just appreciate that with SPT, we look at N or N60, but with CPT, we look at these parameters, and the QC, QS, friction ratio, or a combination of Q, F, and B. So now the question is, so we have all these parameters from the CPT test. How do we use this to see whether ground improvement was successful? Well, before we look at the actual parameters, let's just look at the magnitude. So with cone resistance, friction ratio, and excess pore pressure, these are measurable parameters. Friction ratio is the ratio of QC and QS, right? So you can use these parameters to deduce what type of soil you're dealing with. Now, for example, for cone resistance, for very weak soils like organic soils or anything subjected to virgin compression, NC, clay, you'll have very low resistance. It's not over consolidated soil, right? For sand and gravel, it's quite strong, quite frictional, so you'll encounter very high cone resistance. And likewise, you'll have these same trends for friction ratio and excess pore pressure. So what I want to stress is that you can look at these parameters to assess what type of soil you're dealing with. And typically, you would get this kind of readout, right? You would get everything in terms of depth, tip resistance, friction ratio, pore pressure, and if you have other sorts of instrumentation on your CPT probe, you can get stuff like resistivity, right? Friction ratio is a ratio of stresses, right? That's why it says low percent gravel, because it's a ratio. Now, for CPT testing, you can also get indication what type of soil you're dealing with. Now, just like SPT testing, there's a library of empirical information, right? Now, it's quite important that you look at whether this library is relevant and pertinent to your project. You don't want to refer to something overseas in Europe and apply it to Hong Kong. You have to make sure that this data is relevant. The type of soils and the geological settings have relevance to your project. What I show you here are just examples, right? Here's Robertson and Campanella in 1986 proposed soil classification charts. You can probably find similar things for Hong Kong as well. If you know the cone resistance, corrected friction ratio, you can look at this very fancy complex graph here, and you can deduce the type of soil you're dealing with just based on the region. And there's indication of increasing OCR, increasing friction angle, increasing relative density, and degree of saturation. So you can look at the zones here. Now, this is just an example of how CPT data can be used. There are a multitude of classification systems. You don't necessarily have to use total cone resistance, corrected, and friction ratio. You can use other parameters. Unlike SPT, CPT is a little bit more complex. You have more parameters. You have normalized cone ratio. So these were the ones proposed by Roth, remember, in 1984. So some graphs for soil classification use normalized values. As in this case, it's a normalized cone resistance, normalized friction ratio, and you can deduce some semi-empirical relationship to get an index to essentially characterize what type of soil you're working with. So the main point I want to stress is you don't really have to understand this graph because it's a very specific type of geological setting, but you can use the different types of CPT parameters, Q, F, lowercase q, S, lowercase qc to classify your soil. So it varies in literature. So you just have to make sure the classification chart is relevant for your particular project. Likewise, in this case, same thing, but we use Q and B. We use normalized pore water pressure, and we use normalized cone resistance. So normalized cone resistance, normalized pore water pressure, you get some sort of empirical criteria, and you can look off this fancy puzzle of a chart and determine what type of soil you have. And often for a particular geotechnical project, you probably have a self-contained classification system in itself. There are also ways to convert CPT to SPT. Of course, this is very empirical, right? Because both approaches are highly empirical, but you can actually convert it. You'll even see sometimes when you get CPT data, you'll get depth, and one of the readouts with the equivalent n value from the CPT. So there are correlations as well. You can see here that you can use these complex graphs to get some predicted flow counts. So don't be surprised if you're looking at CPT data and you see that there's also a flow count as well with depth. Sometimes you may feel more comfortable working with flow count if you're a geotechnical engineer that's worked in the region for a long time. You may not be familiar with these cone resistance values, but you may be more comfortable with n value of 50, 40, 100, 80, right? So that's I just want to show you that these exist essentially. Likewise, you can get CPT correlations for strength and stiffness parameters. We mentioned that CPT testing is mainly for fine-grained soils, but you can also look at it for cohesionless or coarse-grained soils, that's phi-dash. For coarse-grained soils or cohesive soils, we're often interested in phi-dash, right? So if you look at different correlations here, such as the one on the bottom left from Robertson and Campanella in 1983, they provide empirical correlations between vertical vector stress and cone resistance QC, and you can top off or read off this graph and get some sort of friction angle, phi-dash, to use for geotechnical design. More often than not, for a very complex project, you'll probably obtain enough samples to do your own triaxial test, to do your odometer test, to come up with your own correlations that you'll continue to use for a particular line reclamation project, should it be large enough. Likewise, if you don't want to use cone resistance, you can also use the normalized tip stress from Roth to use this empirical relationship. Now, this empirical relationship is interesting. They take a bunch of measurements from various projects, and you get some sort of fitted relationship here, and you can draw off phi-dash. Now, the key thing to understand is make sure that this is relevant for your geotechnical setting, soil type, mineralogy, and understand that this is very empirical. So don't try to just go in the literature, pull off something and use it for your project or routine design. Try to use information that's highly relevant for your site, similar projects done in the vicinity of your project. Then you can take that data, extrapolate it, and get geotechnical correlations for it. Just like for cohesive soils, you can get a bunch of correlations for cohesive soils. For cohesive soils, perhaps the most commonly used correlations include something we call cone factor, NK. It's not really a constant. It depends on, well, it's highly empirical. It depends on a plethora of issues here: geometry of cone, rate of penetration, soil type, and also your undrained shear strength. But the key point here is you can get direct correlations of the undrained shear strength that we would use for routine geotechnical design. This is perhaps the parameter we care about the most. Do you remember when we were carrying out the drain example? We wanted to check if the reclamation would fail. And to check if the reclamation would fail, just with the fill surcharge reloading, we had to check the strength of our soil compared to the undrained shear strength, right? So this parameter can be extrapolated from CPT data. The cone factor can vary anywhere from 10 to 18, can have an average of 14. If you want typical parameters, it looks something like this for NC clays at the top, and more complex soils with less relevance to us, such as fissure clay and glacial clays. So some degree of empiricism here using these cone factor correlations to get undrained shear strength, but that's usually how it would be achieved. So I'm just tidying up this module here. With cone penetration test reporting, you'll see something like this from your contractor. You'll have something with depth, and you'll get those values we talked about: tip resistance, so this is corrected, sleeve friction, pore pressure, friction ratio, and there's equivalent N60 here. So they try to convert CPT data to SPT data. And using whatever correlations available, you can classify the type of soil you're working with. If you look at some of this data here, you can see that there's abrupt changes in pore pressure. So anything that abruptly increases in pore pressure is probably a very impervious layer. And anything that drops is very pervious, so probably sand or silt. This is, of course, subject to interpretation. You have to cross-check it with the geology that you find out here. So when you have time, you take a look at the geology shown with the colored contours here and try to think about and relate it to the pore pressures and tip resistance. Tip resistance would, of course, increase for very stiff clays, very strong gravel, friendly material. So you see tip resistance here can increase and then decrease as you get to softer soil. So this is typically how cone penetration testing looks like. Now, throughout the rest of our course here, sometimes we'll refer to SPT or SPT data. So I hope this module is useful so you understand what SPT and CPT data is, how it's used to get strength and stiffness parameters. So this module that I introduced here is just a slight detour from our ground improvement because I think it's useful. Whether you like it or not, you'll deal with CPT and SPT if you're a geotechnical engineer in Hong Kong. So it's nice to know how these parameters came about, particularly SPT. As a good engineer, you should know what this N value means. Is it high, is it low, what type of soil? Is it CDG, what's the typical N value? CDT, colluvium, what's the typical N value? MD, what's the typical N value? So I hope this is useful. So to summarize everything we talked about for this module, this slide is quite important. There are severe limitations with both of these methods because they're highly empirical, but they have their own charms or advantages. SPT is very straightforward. If you have an automatic hammer, it's even more straightforward, but if you have one of those pulley devices, probably more labor intensive. Even if it's labor intensive, the concept is quite simple. You just count how many blows and you measure the penetration of your rod. And the technicians can do that quite well. SP devices don't have electrical components, it's purely mechanical. So you could say that's an advantage, but it's also a disadvantage, right? Because you have energy losses, right? And you have different forms of mechanical SP devices that can cause discrepancies between SP tests. SP testing is better than CPT in that you can get soil samples. You can get some soil inside a split spoon, even though it's highly disturbed, and you can only have limited use of the soil. There are probably way more correlations that you can use in Hong Kong with SPT data and values because we construct the land a lot more than we do offshore with marine deposits, right? So if you look in the literature and existing projects, you'll see a very rich database for blow counts for SPT compared to CPT for strength and compressibility. SPT is a compressive method, dynamic compressive method, so it can sometimes penetrate a very dense granular material, whereas CPT only moves at 10 millimeters per second with limited push and stress, so sometimes you will get stuck with a CPT. See, for the CPT, in terms of advantages, you don't need to continuously bore, remove the auger, replace with split spoon, bore, and repeat test and so forth. You just continuously push in this probe in the ground. So you could say it's faster, but it's probably more expensive. It's perhaps even simpler than SPT in that you minimize the effects of human error, and you might get more repeatable results for more homogeneous sites. as the point says, you only really get interruption when you have to add those 1 meter rods inside the truck, which seems quite trivial. You get continuous measurements where you can detect very thin lines of silting sand. You can add all sorts of instruments to your CPT, inclinometer, gamma, pH, salinity, backscatter. So you can measure a lot more compared to SPT, probably because you can actually install instruments on CPT without damaging it, because SPT is a very violent custom test. Now, in terms of disadvantages, both of these methods will still fail you if you encounter boulders and core stones in the ground. SPT might fare a little bit better, might be able to smash through it, but if it's a very large inclusion, you'll still be stuck, and you'll get 100 blow count or 50 blow count, and you have to terminate. You can probably see from the SP data that we only use one value, n. We try to correlate n with everything, so there's likely to be more scatter with the correlations. And if the correction is not done properly, let's say each of us in this room do an SP test with a different SP device, there can be several orders of magnitude of difference in our obtained n values for the same site. And bullet point 3 says non-standards and sounds. Yes, what's the termination criteria? If you just superficially look at the GI report for 2 sites and you look at the n values, you have to first ask yourself what device was used, how did they correct for N60, what was the termination criteria before you compare these n values. Last but not least, for SPT, we mentioned, although you get samples, they're highly disturbed. For CPT, you're in a lot of trouble for very strong frictional material, gravel or very stiff clay. Mobilization of SPT is slightly more expensive. You have to have a rig, a barge, and since it's not as common as SPT testing, you need a specialist operator to conduct tests, and this can be more expensive. Now, even though we mentioned that you can detect lenses of silt and sand, this may not be the case if this layer is too thin, because the rate of penetration might exceed the scale of the permeability for diffusion, and you might not even detect it. So that's perhaps the limitation of CPT. Last but not least, I think both of these methods are highly empirical. You're basically plotting a bunch of these parameters against well-established geotechnical design, strength and compressibility parameters, and hoping you see something. And what does that mean? It means that the correlations are very site-specific. You cannot easily take something from London and use it in Hong Kong, and vice versa. So that's more or less all I want to talk about for in-situ testing. So we can end here, and in the next class we'll jump back to another form of ground improvement called replacement, where we look at bearing capacity of shallow formation. Thank you.